In this lecture, we're going to learn about a procedure called least-squares fitting. This is probably the most important equation in statistics and some branches of applied mathematics. It's basically how you fit models to data. So before we do this, I want to discuss a little bit more about the matrix inverse. So, actually, before we discuss the matrix inverse, we're going to discuss the normal, like arithmetic inverse. So now, if you look at this equation, if I asked you to solve for x, what do you do? Of course, you divide both sides of the equation by 3. But we can say this in a slightly different way. What if we say we multiply both sides of the equation by the inverse of 3, which is 1 over 3, or we can write this as 3 to the minus 1. So over on the left side of the equation, we say 3 to the minus 1, which is the inverse of 3, times 3 times x. And of course, what you do on one side of the equation, you do on the other side of the equation, so then we get 3 inverse on this side as well. And this becomes 1. So 3 times 3 inverse equals 1, and 1 times x is just x. So maybe it seems a little weird how I explain this, but I did it this way because when we get to matrices instead of individual numbers, the concept is the same. We're going to be talking about applying inverses and moving matrices from one side of the equation to the other in the same way. The reason why things are a bit tricky with matrices compared to this little example is that you cannot just divide by a matrix. It's not so simple. So here you can divide by 3. With matrices, you can't divide by a matrix. So instead, we multiply the matrix by this thing called the inverse of the matrix, which is conceptually the same thing as this. Now, of course, the number 1, this is like the neutral number for numbers. For matrices, the neutral matrix is called the identity matrix, which you learned about in the last lecture. So the identity matrix is a matrix that has, so it's a square matrix. It has all 1s on the diagonal and all 0s on the off diagonals. And the important thing about the identity matrix is that the identity matrix times any other matrix or any other vector is that same matrix or that same vector. So it acts like the number 1. Okay, so let's see this. So now we have these two matrices, A and B, and we say that when we multiply these together, that gives us the identity matrix, so I. So now the question is, how do we solve for B? So to solve for B, we need to move A, or somehow get rid of A from this side of the equation. So again, we can't divide by A, but what we can do is multiply both sides of the equation by A inverse. And now we get A inverse times A over here is just I. And A inverse times I over here is A inverse. So in fact, we just came to this kind of a bit circular conclusion that that B must be the inverse of A, which is sort of how we define the matrix inverse. The matrix inverse is the matrix such that when it multiplies this matrix, gives us the identity matrix. Here you can see a numerical example of this. So here's the matrix A. This is the identity matrix, of course. So now the question is, what is B, or what are the values of matrix B? So it turns out that these are the values. So this is the inverse of matrix A. And the reason why this is the inverse of matrix A is that when you multiply this matrix by this matrix, you get the identity matrix. Now, if you look at this matrix carefully, you might notice that to get this, you can swap this diagonal and change the sign of this diagonal. So that's a trick that happens to work for 2x2 matrices. There's even another step in here that I didn't tell you about, which is that we had to divide this matrix by something called the determinant, which in this case happens to be 1. So in this very simple example of a 2x2 matrix with integers, it's easy to see what this trick is to compute the inverse. But actually, computing the matrix inverse is a little bit more involved. It's a little bit trickier. There's several ways to do it. I'm not going to talk about any of those ways. You can look them up online or work your way through a linear algebra textbook. The important thing there's two important things that I want you to know about the inverse now for this lecture and also for future lectures on generalized eigendecomposition. One is that the matrix inverse, or only matrices, not all matrices have an inverse. Only certain matrices have an inverse. In particular, only square matrices have an inverse, and only square matrices that have full rank. So all of the columns are linearly independent. So matrices that have these two special qualities have inverses, and other matrices, rectangular matrices or reduced rank matrices, do not have an inverse. They do have something called a pseudo-inverse. We'll get to that later. But they don't have a full inverse. The second thing that you have to know is that the main function of inverses for our purposes is to be able to solve equations like this. Basically, to get rid of a matrix multiplication from one side of the equation in order to isolate another matrix or another vector. So this is what we're going to be using the matrix inverse for. All right, so let's see this in MATLAB. So here I have this matrix. I think it's actually the same one that we just had in the PowerPoint slide. So, oh no, it's a different matrix. So the function to compute the matrix, or the inverse of a matrix, is called inf. So it's pretty easy to remember. We can run this cell and see this is a visual depiction of matrix A and matrix A inverse. And when these multiply each other, you get the identity matrix, which it looks like this. So here we can see this is A and then A inverse. So here's an example of where we have simple integers, but the inverse turns out to be not exactly containing integers. So now we can see A times A inverse is the identity matrix. So it's ones on the diagonal, zeros on the off diagonal. And it turns out that this also works the other way around. So A inverse times A is also the identity matrix. This may seem strange to you, but it turns out that computing the inverse is not always perfect. There's some numerical inaccuracies here, but that's okay. This is as close to zero as any computer or any human being will care about. So I briefly mentioned this thing called the pseudo-inverse. So it turns out that although not every matrix has a real inverse, all matrices have, or you can compute something called the pseudo-inverse, which is the closest thing that you can get to the inverse. And so if you have actually a full rank matrix, that was, I guess this is supposed to be the thing we start with. So now A is a full rank matrix. You can see this column is linearly independent from this column. And now we compute the inverse of A or the pseudo inverse of A. Those are the same thing because this is a square matrix with full rank. But now we have this other example where A is a reduced rank matrix. So the rank is just 1. There's multiple ways to see that. You can see that both rows are identical. So this row is a scalar multiple of this row where the multiple is 1. Or this column is a scalar multiple of this column. So anyway, now we can see this is a reduced rank matrix. It's also called a singular matrix. And so if you try to invert it, you'll get this warning. And the warning is that the matrix is singular. So the matrix cannot be inverted. However, MATLAB can produce something called the pseudo-inverse. So now we can see that pseudo-inverse times A, you expect this to be the identity matrix, but it's not the identity matrix. In fact, what this is as close to the identity matrix as you can get, given that A is sort of, it's a reduced rank. It's a bit of an ugly matrix. Okay, so that's a bit about the matrix inverse. Now let's do something else. So now we're going to learn about least squares fitting in the least squares equation. So here's our situation. This is our problem. We have this line A and this point B. And what we want to do is find the position in A, like the fraction of A or the point on A that will get us as close to B as we can possibly get while still being on the line, right? So we just want to find where on A can we get as close to B as possible. Obviously, that point is not going to be up here, right? This vector is really long, and it's obviously not going to be down here because this is really long. Somehow, you should have this intuition that the point should be, the fraction of A should be somewhere around here. And in fact, you might know this already, or at least will believe me, even though I'm not going to prove this to you right now, that the closest point on A to B is the point such that when you draw a line from B to A, it intersects A at a right angle. So it would look something like this, and this is the 90-degree angle. So now our goal is to find this point here, or in other words, this scalar, the fraction of A, that tells us where this point is. So we'll call this this fraction x. So the thing that we're trying to solve for is x. Now, so one more piece of information. This vector that goes from B to ax is the way you derive that vector, or the equation for that vector, is b minus ax. So that's just the difference, the subtraction of b, which would be a line that goes from the origin to b, and the line that goes from the origin to ax. So that subtraction is called b minus ax. So that's this vector. So my question for you now is, what do we know about the dot product between a, so this vector here, and this vector here? So we know, so I told you that these meet at a right angle, which means that they are orthogonal, which means that the dot product between these two vectors, a and b minus ax, is 0. It needs to be 0. And that is the key insight that leads us to everything we need to know, or at least, the basic formula of least squares. So that equation looks like this. So we have the dot product, so we assume that these are column vectors. So we have this vector a and this vector, this one here, b minus ax. And we know that the dot product between these two guys has to be 0. So that's good. And now what we want to do is solve for x. So it turns out that vectors and matrices obey the distributive law, which means we can expand this to look like this. So now we can rewrite this first equation to say A transpose B minus A transpose A x equals 0. And again, we want to solve for x. Of course, the next step is to put the A transpose B over here. So now how do we solve for x? How do we get rid of A transpose A? Actually, this is easier than it seems, because A transpose A is a dot product of A with itself, which is just a scalar, right? It's just a single number. So we can actually divide by this. This is not dividing by a matrix, which we can't do. And in fact, this is really just the length of A, or the length of A would be the square root of A transpose A. So this is the squared length of A. So we can divide both sides of the equation, and this is nice. Now we got x. And so the interesting thing about this formula is this tells us for any point B anywhere in this space, this is the formula to get the closest point on line A to that point in B, and it doesn't matter where B is. It can be anywhere in this two-dimensional space. So why do we care about this silly little problem? Remember, I've mentioned in the last video, and also in some other lectures a long time ago, that it's useful to think about these toy examples in 2 dimensions because you can see the geometry. It's very intuitive. It turns out that this is exactly the same formulation that we use for least squares, except in practice, in the real world, least squares happens in a much larger dimensional space. But the idea is the same. So A is going, well, let's see what happens. First, we'll see how this works for matrices instead of vectors, and then we'll see how this translates into statistics. All right. So now things are almost the same, except instead of having vector A, we now have matrix A. But still we have the distributive property. Oh, and so X is now not a single number, but X is going to be a vector. And also B is not a single point, but it's going to be a vector. So then we get back to this thing, and then this thing is easy. We can always subtract matrices by both sides. That's no problem. The difficult part is when matrices are multiplying something and we want to get rid of that multiplication. So the neat insight here is that although matrix A on its own may or may not be invertible, it might be a square matrix, which would make it easy to invert, but it might not be a square matrix. But that actually doesn't matter because A transpose A is always a square matrix, and it's also always a symmetric matrix. And in fact, when A is a data matrix, so in this case A would be for example, time points by channels, then A transpose A is a covariance matrix. So although A may or may not be invertible, and certainly for data covariant for a data set, A is not going to be invertible. A transpose A is a square matrix, and if you have a full rank data matrix, then A transpose A is also invertible. So this is nice. This means that we can multiply both sides of the equation by the inverse of A transpose A. It may seem a little bit weird at first to have an inverse of these two matrices, but actually the multiplication is one matrix. So I could have had an intermediate line that said K equals A transpose A, and then we have K inverse. But anyway, so this is the inverse of this, which means all of this, these 4 matrices together, this all reduces to the identity matrix. And of course the identity matrix times X is just X. And then here we're left with all this stuff over here. So this is A transpose A inverse times A transpose times B. If I would just show you this equation right off the bat at the beginning of the lecture, probably you wouldn't know how to make any sense of it. But I hope that you followed everything from the last slide and from this slide, and you see where we got this. So this is now our equation for X. And I hope you can also see that this equation is really similar to the one in the previous slide, right? The one in the previous slide, I'll go back quickly. So here we had A transpose B over A transpose A. And here in this 2D case, two-dimensional case, A transpose A is the dot product, so that just reduces to a single number. So there the division is okay. Here we have A transpose A, and this is like dividing by A transpose A if A transpose A would reduce to a single number, the dot product. But this is a matrix multiplication, so this is a full matrix. So it's multiplying by the inverse. So I hope that makes sense. In MATLAB, you would implement this equation by this code. And now it turns out that inverting matrices is kind of difficult for computers. And the bigger the matrix, and like the more detailed the matrix, the harder it is to invert. And so in general, MATLAB tries to avoid actually computing the inverse whenever it possibly can. So in fact, although this equation makes sense theoretically, in practice, computers don't want to compute the inverse. So MATLAB has a bunch of tricks that it uses to implement this equation without actually taking the inverse of A transpose A. And again, I'm not going to go through what those tricks are. They're not like incredibly, unbelievably sophisticated. They're pretty, some of them are neat, but it, these are sort of details that are outside the scope of this. This is the important equation to understand. And actually, what you do in MATLAB is use this backslash character, and you can think of this as meaning that we take the inverse of this matrix and multiply it by this. So you don't need to worry too much about the details, but in fact it's not technically the matrix inverse that gets computed, but that's okay. So, and maybe this looks familiar to you, maybe you have seen this equation before. In fact, you may not have seen the equation before looking like this, ax equals b. If you've taken a stats class, then you've probably seen something that looks like this. So x times beta equals y. This is actually the same equation, and we could have gone through it the same way, but for some reason this is the convention in linear algebra, this is the convention in statistics. And if you remember your stats class, then you might also remember that we have specific terms for these matrices and vectors. So this X is called the design matrix. It's a matrix that contains columns for each of your independent variables and rows for each of your trials in your experiment. And then we have beta, which is the parameters. So these are like the regression weights, they're also called. And then we have y, which is the observations, or this is the real, the actual data that you measure, which would be one value per trial. And so this beta vector would be one value per column in the design matrix. So here's just an example of what this might look like. So this could be a design matrix. This first column is, it contains all ones, and it's also called the intercept. Or other people call it the constant term or the offset term. These are all acceptable terms. This is actually a little bit comparable to the zero frequency component of a Fourier transform, in that the intercept captures the mean offset of the data. So, and then here we have a linear term, and I don't know, maybe this is like trial order if you want to look for some kind of, if your subjects are getting practice effects maybe, or if they get tired throughout the task. 5 trials must be a very long experiment. And here, so these are, just some other variable. But the point is that you can see that matrix A has 3 columns for 3 independent variables. The number of rows corresponds to the number of trials. And you can also see that A is a rectangular matrix. It's not a square matrix. A is not going to be invertible on its own. In fact, the rank of this matrix would be 3. So in B would be the observed data. So maybe this is, I don't know, alpha power. I guess it would have to be normalized alpha power on these different trials. And then to solve for, well, here I still have x, but in this formulation we would solve for beta, and then this is the equation to solve for beta. It gets a bit confusing, right? That here x is a, and here x corresponds to beta, but whatever. So I would like to go back and work through this least squares equation once more, now that you have seen this example with actual numbers in here. So the idea is that we want to, we start with this equation ax equals b, or I guess I should have written this with the statistics notation, x times beta equals y, but that's okay. And now what we want to do is solve for x. So how do we solve for x? We need to get a on the other side, or we need to get rid of a from the left side of the equation. But we cannot just divide by a because it's a matrix. And we also cannot just multiply by A inverse because A does not have an inverse because it's not a square matrix. So what do? We use this trick where we sort of convert A into a square invertible matrix by multiplying by its transpose. So we multiply this side by A transpose, and this is great because this is now an invertible matrix, which means we'll be able to get rid of it from this side of the equation. And of course, whatever you do to one side of the equation, you have to do to the other side of the equation, so we have to multiply the right side of the equation by A transpose. And now we can take or multiply the inverse by both sides, and then we get to exactly the same equation as before, just with a slightly different, explaining it in a different way. This, I think, is always nice in math, and in particular in applied math, when you can derive an equation or see that an equation works using multiple different ways. It helps you sort of internalize what the equation means and what it's doing. Nonetheless, it's the same equation and the MATLAB code is the same. So let's take a look at this in MATLAB. Here we start with a very simple example, 10 numbers. And here we're going to generate some data. So it's going to be linearly spaced numbers between 1 and 3. And actually, this is an example of bad programming on my part. This should say n, right? Because here n is soft-coded, which is good. That's what it should be. But here n was hard-coded to be 10. So it would work in this case, but if you wanted to try it with 12 numbers, then this wouldn't work. So shame on me. Anyway, so B is going to be linearly spaced numbers between 1 and 3 plus a bit of noise. Here is our design matrix A. So you can see it's a column of all 1, so this is the intercept, and then it's a column of linear indices going from 1 to n. So this is going to capture a linear effect. And now we compute B. And you can see this is exactly the same equation that we had in the PowerPoint. And I hope you still have this picture in your mind of trying to get from point B onto line A and realizing this key insight that the closest point on line A is such that line A is orthogonal to the vector that goes from line A to B. And so that was how we derived this equation. Anyway, we can plot this, and we can see here's our observed, in quotes, of course, we didn't actually observe these data, but our simulated data in the blue dots, and then the red stars are the fitted data. So this is the least squares best fit to the data. So this should look familiar. It's important to, so I don't have a lot of examples here of where this doesn't work, but it's important when you're computing these models to plot the data like this, plot the original data and plot the fitted line, because it's very easy to make an innocent little MATLAB mistake and end up with the incorrect result. So, but the good thing about plotting is that when you make a mistake, usually when you plot it, you will, nearly all the time, if you make a little innocent programming mistake, when you plot the data and look at it, you would see that something is obviously wrong. Maybe this best fit line might be all the way up here, and then you would know that something went wrong. All right, so this is a fun little toy example. I want to now do a real example with some EEG data. So we're going to load the sample EEG data that we've been working with many times. This cell here just extracts the reaction times from the epoch information. If you are familiar with the EEG lab format, then this might make sense to you. This might look familiar to you. If you're not, then you can go through these two lines if you like, but this is just how we extract the reaction times in milliseconds in this particular format of data. But that's not the important part. The important part is this design matrix. And this is, again, so it's just 2 columns, so 2 independent variables. First is the intercept, it's all ones, and then next is the reaction times. And here I just had to transpose the reaction times because the way it gets computed here is it happens to start off as a row vector, so we need to convert it into a column vector. That's more housekeeping than anything really meaningful. All right, so now what are we going to do? What we want to do here is see if we can identify time frequency dynamics that correlate with reaction time within this one subject's data. So we want to see, across trials, for example, when the subject responded faster, was there more alpha suppression, something like that. So therefore what we need to do is extract the time frequency information. We're going to do that from one channel, 47, and I encourage you so this is channel FCZ, which is like a mid-frontal electrode. I encourage you to try this with other channels and see how it works. Elsewhere over the head, I picked this example because I know it's going to work. So this is all code that you've seen before. There's nothing new in this code. The only thing that might be a little bit different is that typically we average power over all the trials. And here we're not. Here we want to save all of the single trial data. So we have this matrix TF3D, which is a 3D representation of time frequency power, and the dimensions are frequencies 30 by time point 640 by trials 99. Okay, and so now what we want to do to make this least squares fitting a little bit easier is transform this 3-dimensional matrix into a 2D matrix. So we could still do this with the 3D matrix, but we'd have to loop over time points or loop over frequencies. And it turns out that, in MATLAB, we can reshape this to 2-dimensional and then fit the model in one equation. So, and then this is the whole thing. So this fits our model, or fits the model to the data and finds the best parameters. And so now let's make some plots of what this thing looks like. So this is our matrix A. Right, you can see it's 2 columns for the intercept and our reaction time term, so an independent variable. And obviously this matrix is definitely not invertible. It's very much rectangularly shaped. But on the other hand, this matrix, so A transpose A, this is a 2x2 matrix, and maybe or maybe not you can see it by just looking at this matrix, but it's actually an invertible matrix. You would know because there's no way to get this column from some linear, some scalar multiple of this column. Anyway, here is our data matrix. So this is what I call TF2D. And you can see here are the 99 trials. And here it looks kind of funny, but what's actually happening is these are time frequency points. So there's 30 frequencies and 640 time points. So when we stack them all together, you can see it's going through all these time frequency points all the way up here. All right, so now you must be very excited to see what the results look like. Let's see, where are we? So we need to convert these back. So this is a 2 by 19,200 matrix. The first dimension, this corresponds to the parameters, the beta coefficients for our independent variables. And the first one is the intercept, and the second one is the RT, and it's the RT that we really care about. This is the thing that we want to look at. And then this second dimension, where are we? The second dimension is this time frequency expanded series. So here we just reshape this back to frequencies by time points. So This just facilitates the plotting. And here are the results. So this is a plot that initially you might look at this and think that it's something like a time frequency power plot. But we have to be careful about interpreting this. This is not time frequency power. These are like regression weights, or you can think of them as similar to correlation coefficients. We could scale these to be correlation coefficients, but these are covariance points. But the way we interpret that, the color, is that it reflects the relationship, the sign and the strength of the relationship between time frequency power over individual trials and reaction time over individual trials. And so the way we would interpret this is we say that trials that had a longer reaction time also have larger theta power between 600 and 800 milliseconds. And similar, also those same trials, so trials with, well, we can interpret this the other way maybe. Trials with shorter reaction times or faster reaction times also had less theta power between 200 and 400 milliseconds. So whether this finding is sensible and interpretable, of course, depends on what's happening in the experiment and what kinds of theories or hypotheses you're interested in testing. The point here was to illustrate how we can use, just a real-world example of linear least squares fitting. So I hope you found this lecture informative and interesting, and we'll continue on in the next lecture with more fun tools that we get from matrix analysis.